That's amazing. Yeah, that was amazing. Yeah.
Why there is the whole procedure looks extremely complicated. Oh no, this is bad. So we should call Alicia. We can't get too late. Last time it's automatically works. Is that right? I can call Alicia. There's only one option.
So welcome to our first high energy theory seminar for the fall semester. And just a reminder that we've been given permission, I think, to be allowed to have lunch in the seminar.
Not have lunch.
We are allowed to have lunch.
Allowed. Okay.
Right? So that's the university rule. So you can bring your lunch again if you want. And so today our first speaker for the semester is Merab Gogberashvili. Merab is a professor at the Tbilisi State University, and that's in Georgia. And that's the country for the people that don't know, the young people, not the state. All right. So he's come from a very long distance, and today he's going to tell us about LIGO signals from the mirror world.
Hello, it's my pleasure to be here after 20 years. I have said that exactly 20 years ago. But it was different. Not building, but it was one seminar, round table, everything is wonderful. So I will speak today about some idea about this type of neural particles in your world and some consequences of this idea. The plan of my talk is 4 chapters, different colors. The first 2 parts is more introduction, historical, and some idea about discovery of parity relation in the idea of mirror world. Then the history of gravitational waves, theory and detections. And then analysis of LIGO signals. And some astrophysical problems with their detection, is third part. And the last one is our idea probably some signals can be explained by mirror matter, which doesn't maybe exist in our universe.
How is this book? I mean, do you want to use the
Do you
mic?
hear me?
Yeah, because we can switch to the mic. Yeah, we have a mic.
Oh, no,
I think it would be better. If
Yeah, let's switch to the mic. Yeah, no, the mic is should be down. Yeah.
I think better to speak louder.
Yeah, yeah.
What is GW?
Gravitational wave.
Gravitational waves?
I will explain all this.
Okay.
It is standard description of LIGO signals, this year and number. Is this better?
No.
Yeah, okay. We'll start with parity violation history in particles. It reminds that also tau theta puzzle problem in 50s of 20th century. It was discovered two particles. They think it was different strange particles, which have different channels of decay, and but they have same mass, and later it was appeared that you just same meson, and this it can decay in two channels with violation of parity. It was the idea of Lee and Young that weak interaction probably don't conserve parity. At that time, it was nobody agree with this, and they explained to Dr. Wu idea of experiment, and this famous experiment of Wu in beta decay of cobalt 60 in magnetic field, when they show time and asymmetry in left and right. And also is against of this idea was Pauli. So this is famous his phrase that God is not weak leg-handed. But then appears that we have some direction in space, and we need some idea to explain how it's possible that we have isotropy and homogeneity that we observe, but particles, they have some asymmetry in space. And after this come idea of Li Yang that we need some particles, right particles, and we can restore the symmetry in space if we have opposite chirality particles or right particles. And okay, they obtain Nobel Prize on this idea of violation of weak interactions, but they first suggest that probably we have some right helicity particles involved, and we have symmetry in left and right in this space, in that space. So the coordinate is not important. Important how we define parity and particles after reflection. Then next year, it was idea of Landau and also Lee that probably we don't describe correctly what is parity. Is we have a special operation in Dirac spinors, we change parity, and probably that right particles are not p-symmetric particles, but CP-symmetric particles. So we need to change also antiparticles and helicity together, and then we can restore symmetry of coordinate transformation. It was an elegant way to restore symmetry, because Dirac theory, we know that there is a CP invariant, But later also it was discovered that CP is also not good symmetry. Particle physics, example of decay of omega plus, and which after C we have not this reaction, and P we have this, and also we have not this. So one of the example of CP violation. And then this idea about left-right symmetry again become problematic. It's a nice picture of Escher and explanation of CP relation in the diagram. Maybe you have seen this picture. We have two ingredients here, color and direction. So we can say it's a C symmetry and P symmetry, and it is CP symmetry transformation. And the hand-on conservation. We have no anti-volt in some case. So somehow our universe don't respect this symmetry, discrete symmetry for particles. And now more modern history about this. In the 60s, some people from Russia, they suggested that we have some hidden sector or mirror world, now we call now, which can restore this symmetry. And with these particles, our theory can be left-right symmetric. Also, they also calculated that this mirror particle cannot interact directly with normal particles. Otherwise, we have problems because we have doubling of atomic level on pionic states, or so many other problems. Everything is doubling. So only possibility that left and right particles are not have not common coupling, only by gravity or very weak coupling. And they are exact symmetry in masses and in charges, but they are separate. So
the connection between these two worlds is only through gravity.
Through gravity or through mixing. I will talk about this, neutral particles mixing probably. But what more important for my talk is the gravity.
But so, even to mix neutral particles, you need some interaction, right?
Yes. So for us, we told that important is particles and antiparticles, but somehow universe said important is left and right. And we have left photons and right photons. They are separately and they cannot mix. Maybe there is some kinetic mixing between this left and right photons, but this is not normal photons. For us, photon and antiphoton is the same particle. But left photon and right photon, different particles. So why is this possible? We don't know. If right world exists, maybe they are in the same universe. It is not a parallel brain or something. It's here, but we don't see them by ordinary interactions. All interactions are singlet and neutral. We cannot couple these mirror particles if they exist. So it was idea appeared in 60s about mirror world. And now about cosmology. If such particles exist, of course, we can use it in astrophysics, cosmology, in particle physics. And then I want to mention Blennikov and Khlopov's paper in the 80s, and Khlopov's postdoc, Veregiani, who then continue still now, is one of the leader of this mirror particles experiments and pushing this idea. So idea is that we have two class of particles, two standard models, left and right. So we have ordinary particles, we call O or capital, and mirror particles. And there's a different name in different different papers. Somebody it's called shadow matter or Alice matter. So Alice in Wonderworld from this book. So it's because of mirror, some mirror particles have different properties. So at first it was supposed by Veronica Hopos that their cosmology are exactly the same. Yeah.
Exactly the same copy, then cosmologically it's a problem, right?
Yes, yeah.
It's a huge problem, right? So
yes.
you have to break the symmetry. So.
Yes, I will speak about this. But at the beginning, first model, they symmetrically, they think that all conditions are same, constants and matter and same cosmology.
Can these mirror particles form dark matter in our universe?
Of course. First idea, if you have some shadow matter, it should be dark matter.
And our universe correspondingly for
them is dark matter.
For them.
Yes, yes. It is main idea, of course. So I want to remind also the old GATT models, GATT unification models with a left-right symmetry. So if you have two copies, left and right, and we have two standard models, we have that group is larger, which have left and right symmetry, and first model with left-right symmetry is Patisala model. It was even anticipate Glashow's SU5. It was first in 74 because everybody worried about this asymmetry. Nobody understand why, as Pauli said, why God is left-handed. So it's natural to think that something we miss. Somewhere there's a right world. And this first model of unification group is SO4, so SO left and SO2 right. Of course, there is another particles, but main what I mentioned here because it is left-right symmetric grand unification model. Now motivation. I already told, but let me emphasize this. So at first, it's elegance that we need some symmetry. People like symmetries, and when you have some violation, you need to restore somehow. And if we restore this, then we need mirror matter. Then historically, Lorentz-Wiley invariance dictates that we need Dirac theory and antiparticles. And then the exact parity symmetry, if we restrict our theory, then introduce mirror particles, and probably they exist. And now how we can use them. In cosmology, of course, dark matter is mentioned. Then high energy cosmic events, and if you have some mirror planets, mirror stars, they can collide, and suddenly you don't see, but suddenly you can get signals from empty space, empty volume of space. In astrophysics, MACHOS, it is a massive object in galaxies, which we see by microlensing, but we don't understand their physics. Maybe they are mirror stars. There are isolated planets, stars, okay. Even some objects with bombarding the Earth, like Tunguska meteorite. There is a papers people want to explain by mirror comets, missing comets, and which even can bombarding Earth, and it is mirror matter. And these real papers in real journals, so you can, if you're interested, you can read such a papers. In particle physics.
On Earth, if they bombard the Earth, what you see, just tidal forces or something?
So you
go right through the Earth, right?
So they have no electromagnetic counterpart, but by gravity, then they can interact with some object by gravity. And
when they, I mean, if they're comet sized, wouldn't they start upsetting a little bit the orbits? And
So there's some
or something.
there are some missing comments. You have some gravitational influences in, if you know, planet X.
Okay.
So a lot of these things you can explain by mirror matter.
But not, but bombarding the Earth, we would know it, right?
Yes, yeah, but we have some strange events like Tunguska, I told, and others that you cannot explain by ordinary comets because they disappeared. You have a big.
But how do we know it? Because they have only gravity interaction.
Yeah, but if it's
so if you have this bottle and you smash it against the desk, it's not the gravity interaction which produces the effect, right? It's electromagnetic interaction.
If it hits the ocean, if it hits the ocean,
yeah,
it's just the gravity would create a tidal wave or something, right?
Well, it depends on the size of this.
We are much more sensitive to gravitational perturbation, like all the GPS systems have seen that.
That's what I was just saying.
Yeah, LIGO would have seen that. It's a transient signal induce a power.
So there's idea that probably we have some mirror planets, mirror stars nearby. We don't see them. So
that's different than bombarding. I'm really talking if it's
coming
and hitting
also
the
they can be in the also in the core of the Earth there can be mirror matter. In the Earth, in this sun.
But it's static. It's there. I'm thinking of something coming and going through and out the other side, right? Like Misha says, it'll go right through, but there's still an interaction.
Well, if it is very huge piece,
the comets are pretty big.
Then of course it will have an impact through gravity. Right. Just yes.
And you don't see any pieces of this. You just see. Yeah. Okay. So it's a shadow matter. And now in particle physics, so there are several reasons why I need second Higgs or neutrino mass and mixing with something stereo neutrinos, or there is the anomalies in experiments with orthopositronium or missing of neutrons. You know, the recent experiments that 5 sigma signals of missing of neutrons. Nobody can understand this. And the main idea is that there is a mixing between neutral particles and mirror particles from our mirror world, and then you can explain this disappearance. The orthopositronium is photon mixing, and in neutron missing. Neutron have no charge, so you can mix with mirror neutrons. Okay, it's some experiments and ideas people explore in connection with mirror world idea. So, just summary about mirror particles. Two properties. They don't couple or very weak couple with standard model particles. We have second standard model, which are singlets to use each other. But at a large scale, at cosmological scale, maybe it is big impact or big impact in particle physics. So that we will speak as a last part of my talk. And the idea that it's contact with us, interact with us by gravity or mixing, which I already mentioned. Now problems. That first idea, what was a symmetric mirror and ordinary world, is then we have these two problems that we have problems with Big Bang nucleosynthesis because everything is doubling, and helium number of helium is more than 28%, which is not observable if you have mirror particles at that time the same amount. And also to explain dark matter, you cannot do this. And solutions that we need some different temperature after heating for mirror sector and our sector. Then you can solve this problem, restrict the extra result, and then explain some things. So to explain dark matter, you assume the temperature in mirror world is lower, and matter abundance there is higher than in our world. So we have some 5% of the universe is matter and around 25% as dark matter. And in mirror world is opposite. Because in this idea, mirror matter is dark matter for us, and dark matter for them is our matter. So they have dark matter 5% present, and we have 25. So this main idea, this if temperature was smaller than for ordinary matter, we have mirror baryons access, and we can explain all dark matter or part of it. Okay, I go here.
I mean, maybe you'll get to this, but if the cosmology for this mirror matter is just like a thermal bath, it's just redshifting like it like happens for us, wouldn't you expect that like every combination of the mirror matter should just all be relativistic, like radiation? Whereas I think you want dark matter to usually be non-relativistic at that point. Does this like not mess up things like, but like does it give you the correct properties of dark matter, and also does it mess up things like ineffective?
Ineffective is what he just talked about. He said
yes, it's effective dark matter. So
okay,
you should assume
really change
you should yes. Why is it, all this world was created by Big Bang, but why temperature should be equal? You have very little tiny difference in parameters, and it will be radically different cosmology. So if you assume that temperature is a little bit lower, then after heating, you can explain some strange things in our world. So this is the idea. So I finishing this mirror part and go to gravitational wave. So any questions about mirror?
Well, the dark matter is because you're basically thinking that it's the baryons, right? The dark baryons of it. But they would make dark galaxies and things,
yes,
and dark clusters. But
so what you see hollow, it is dark galaxy.
Well,
around us, which is
why not a disk? Why aren't there disks of these things?
No, because it is cooler and it's developed quicker. They have more helium stars, which so they have not spiral galaxies, but spherical galaxies. It is larger. There's more matter in mirror world, and the galaxies are more spherical, not like in our world.
Even in that case, it's not clear that the distribution of the dark matter in that kind of a situation, because they would also have to be aligned, that the dark galaxies would have to be aligned with ours.
Yeah.
But they don't necessarily have to be that way, right?
Yes, but you see, we have some dark galaxies or galaxies without dark matter, but most of galaxies has dark matter. Also, there is a small galaxies which have a problem with dark matter. So any of these things can be better explained if you say that mirror matter is your dark matter. Okay, so it is not my topic, but some people, there's reviews, you can talk how they explain better than, yeah.
These baryons also have to be stable.
Yes.
Stable.
Well,
the proton and neutrons, ordinary.
But it's charged, right? The lowest proton is the lowest. It's a charged state. Lowest one.
But it is mirror charge.
I see. So it have to be charged under the mirror.
That's why I said that's why they form dark galaxies. They would bind.
Just in the usual way.
In the usual way.
Their own mirror states.
Yeah.
False characters.
Yeah.
But so you want the dark matter to be these mirror like protons and mirror electrons, but isn't that like just like, you know, at like recombination, the like baryon density is a small fraction of the total. It's like 10 to the minus 9 of like photon density. Shouldn't the mirror baryons be a small fraction of the total mirror cycle energy density?
So in this model, they suppose that energy density of matter there's 5 times more than in our world.
I guess I'm asking, aren't there a bunch of mirror photons also hanging around?
Yeah, but they're cooler. They're cooler.
temperature is lower, but matter is more
but
matter.
you still have a bunch of mirror.
So I will show numbers what people say
Everything
about
would be the
this.
same. You would go through mirror recombination, but and that might even be at the same time.
Yes.
It's just cooler.
It is strange possibilities that you don't need to introduce some extra dimensions or brains or something. Just from particle physics, you can have some shadow matter here and don't see them, only by gravity. So
We have a shadow planet here with shadow people.
Yeah. So from particle physics, if you just say that I have parity symmetry, you have shadow matter. But probably you have just left-handed particles. Okay, so I go to gravitational wave part. So it is not easy. Theoretically, we have a lot of problems in general relativity. It is old theory, more than 100 years ago, and still survives this, and we use them. But you know that have theoretical and observational problems. On the theoretical side, main is this energy problem. And this is central problem from gravitational waves, because if you cannot describe energy of gravity, then cannot calculate how many energy you can lose and how gravitational waves can take energy. You need some models. And there is some models which we use now in LIGO calculations, but even Einstein was against existing of gravitational waves. And what is the main problem of calculation? In a linear approximation, gravitational waves cannot carry energy. It's very easy to show, like Maxwell's theory shows that the photon cannot take charge because the source is. So if you like Maxwell equations and make divergence, you see that it is zero by definition. It means that you have exact conservation of charge, and in linear approximation, photons does not carry charge. If you want charging photons like gluons, then you need that F should be defined. Also, we have this part, antisymmetric part, and then this is not exactly conserved from this divergence. You can do the same thing for gravity, but in gravity, you have here tensor of energy momentum, and here is a similar combination of.
Please take another marker. This is not seen.
No other markers. Okay, but
There, over there.
That one's going there.
okay, they're similar. If you go to linear approximation, Einstein equation very similar to Maxwell equation, just extra index. And the source here is relative momentum tensor. And if you go this way, make divergence, you see that this is zero, and gravitational wave cannot carry energy in linear approximation. And to carry the energy, you need nonlinear second approximation. But in second approximation, you have energy momentum metric tensor also here. So you need to keep one side of Einstein equation in second approximation, another side in first approximation. And so there are some difficulties to calculate. You have model. And we have energy losing formula of Einstein, which works, especially for binary pulsar. But there is some people, we don't agree with this calculation, with this observation of LIGO. Okay, I don't want to go to details, but I want to say it's not so easy to believe what they observe. And even Einstein was against, as told, and the main efforts of observation start after Feynman's idea that I don't care about what you crazy gravitational people talking, but if I have some bead, sticky bead, and gravitation will go through this bits we call fraction. It means they are temperature, they change temperature, they carry energy. So I don't know how we calculate, but gravitation energy should carry energy. And after this, some experimental efforts to find gravitational waves. It is, yes, at first what might make waves. We have several possibilities. It can be periodic, stochastic, and burst-like or chip-like, which we observe by LIGO, which is from binary systems. This other three is very difficult to observe because of weakness of gravity. And main what we will pick is binary system and this chip-like signals. Okay, this history of detection effort. First experiment is Weber. Is this cylinder, aluminum resonance cylinder. Even he talks that he get one signal, but nobody can prove because no other such equipment, and probably it was just earthquake or something. From LIGO we know how difficult it is to observe, and this is very noisy equipment, and it was impossible to observe waves if it's not fast or very strong. Then in the 60s, also some people from Russia suggested to use interferometers. Yes, it was just idea. And then next step is the indirect observation of gravitational waves, observation of Einstein formula. They're looking for losing of energy of pulsars, and for explanation this they use Einstein formula for gravitational waves. It is exactly matching. So it is indirectly proving that this pulsar are losing energy because of gravitational wave. And it's also Nobel Prize. And then direct observation, we think so. It is LIGO and VIRGO collaboration. Really, it was LIGO because VIRGO don't working at present also. So they are just part of collaboration, but really they don't observe any. And we are thinking that maybe Kagra detector from Japan can be third independent detector. And okay, this also Nobel Prize. And these next missions, first is LISA in space interferometry, is huge triangle in outer space. So I am very pessimistic that it will be launched any time, because first it was 20s and 30s, and maybe it will be 40s, or this will be very expensive project, and I don't know if it's realizable or not at all. But idea is that to send interferometer in outer space and check for gravitational waves there. Now, what is LIGO Observatory? You already know it is a map of existing and planning interferometers. That's two in States, main. There's a GEO in Germany, VIRGO in Italy, which says that it works. Now it's Kagra, which 2 years ago was finished, and in third observation run, they also start to obtain data. And India want to build LIGO-like detector. It is under construction. I don't know. Also expensive project, and India want to spend money on science and wait what they will do. So this observation is half on the Livingstone. Just we called it new era of multi-messenger astronomy, because we have observation on electromagnetic signals, and if their signals are real signals, we first time see something else. not electromagnetic signals. It's just different kind of observation. So it is 2 papers and Nobel Prize of 3 years ago or 6 years ago. It is first run of LIGO. It was started in September, and immediately they found the first signal, which is main discovery, and it was announced then in February of 2016, and it was big boom in physicists. All of you maybe here or direct press conferences, what's happened, so headlines everywhere. And the same year they have another signal, which is confirmed. This was candidate, but then it was rejected.
Excuse me, Merab, do I understand correctly that your point is this gravitational waves came from the mirror world?
I will speak, yes. I want to explain, probably, yes.
So not from our collision in our world.
I want to make astrophysical analysis of existing data and to show that more realistic is not what we see, that is a lot of black holes around us, but more realistic is that there's mirror world and black holes there.
If it's a black hole, then how do you, it's a black hole, right?
Yes.
Everywhere, in all worlds, because they talk gravity.
It is from mirror matter.
But once it's inside the black hole,
You cannot say.
Unless there's some conserved number, right? Some gauged quantity. There's black holes have no air.
Black hole is from matter or for dark matter.
No, but when it's
you don't know. Yes, everything is there.
Yeah.
So same dark matter for me is the mirror matter.
But presumably you also have neutron star then, right? You don't necessarily need black hole, right? Never a neutron star. Right?
Yeah, I will speak about this. Okay, let's finish with historical part. What is now present situation? So we learn if signals from LIGO is real gravitational signals, and we have correct explanation. We have a lot of black holes, much more than we expecting around us. We want, you know, the CMB map, and there is a so-called E mode and B mode. And if we detect B mode, rotor mode, then only possibility is that we have gravitational waves at the beginning, and we can detect gravitational wave by polarization map. This map should be published 2013 and still waiting. I don't know, it's very difficult data to extract from CMB data polarization map. When we confirm we have gravitational waves at the beginning or not. As I told also this LISA satellite, which should be launched in 2037 or 34, somebody optimistic ideas. And this Japanese detector Kagra, which a little bit different, it is not interferometer, which first was reported in November 28. We have already 3 runs in VIRGO, LIGO, and now Kagra. And next for observation run is scheduled for next year, from March. And there is the ideas also a so-called Einstein telescope or cosmic explorer for very high frequency gravitational waves. So it is also on ground project, but it's still project, third generation of detectors. So how many events we have detected? We have 3 runs. We have A and B because of COVID. It was interrupted between runs. And we have confirmed 90 events. It is 84 is most of them is black hole to black hole binaries. There's a 2 neutron star. There's 2 black hole, neutron star, and the black hole. And in mass gap object, we don't know it is black hole or neutron star. It is our interpretation. Signals is very weak and very difficult to extract information from their equipment. But if we do it correctly, it is our interpretation that we see such a kind of object. And from this 90, only one signal is accompanied by electromagnetic gamma ray bars, which was found in the Fermi data. Also, it is a strange situation because when this merger was observed with gravitational waves, then they look on Fermi data and find something close to this date. It was not reverse that they issue something flashing and then you see gravitational waves. No, at first it was observing by LIGO and then they looking on all data and they said, okay, maybe this is the same signal which is accompanying signal for this event. Because you have no localization in the sky. It is long range of the sky from which direction this signal is coming. And matching in time and matching in just half hemisphere. And by this, it was proving that it's the same object. And the main reason is to obtain Nobel Prize for this. Otherwise, nobody can give, because you have experiment, you need some proof, some experiment to obtain Nobel Prize. Okay, I don't know, but now we have a lot of mergers and we don't see anything else, only gravitational waves from these objects.
No, but as you saw, there are only two neutron star mergers, right? And you don't expect any strong electromagnetic.
I will speak about this, but not strong, but something.
From two merging black holes.
Yes, for example, yes, because it should be exactly empty outside, so no matter, accretion matter. You need black hole which have no accretion matter at all. And also,
as I understand, the signal from neutron star was a lucky coincidence in a sense, right? Because
yes, you can calculate probability of this coincidence is 1,000,000 times less than have such a strange signal. Okay, but we want to believe that we observe gravitational waves and we can have extra equation, extra possibilities to observe universe. Okay, now this is famous graph of all these 90 events. So here is the mass in solar mass is logarithmic scale. And here is just x-axis, just for visual, don't correspond to any time or something. There are other this kind of graphics with data, but it's difficult to observe, and so it is symmetric picture. You see what was merger, for example, these two black holes, and it is a result. So they show two merger masses and resulting object merger mass. We have bicolors. This LIGO VIRGO black holes. It is blue. It's, neutron stars. It is this purple, yellow, and electromagnetic black holes. When you see, it is not VIRGO object, just ordinary black holes, and electromagnetic neutron stars. It is just ordinary neutron stars.
So what's the difference between left and
nothing?
right?
Just spread.
Nothing.
Nothing.
It's the same.
Yeah.
Oh no, it's not the same. It's different data, but it's
Just besides the order.
Because if you put on the same,
artistically, make it symmetric.
otherwise you don't say anything, because if you put this data one together, it's very difficult to see.
So what's this mass gap again? Can you remind me?
Yes, I will say. Now I have two mass gaps. It is called lower mass gap and higher mass gap. And I will explain what it means. But there is some theories, astrophysicals, very semi-empirical models, that they say that there are no black holes between 2 and 5 solar mass, and no black hole between 65 and 100, around 100. There's some mechanism of creation black holes. And nobody expect, because ordinary black holes, which I told this is electromagnetic and this neutron star, you see that there's outside of this mass gap. It is maximum of this here, this red one, and this yellow, this lower than.
What are the points without lines?
It is electromagnetic black holes. You observe ordinary black holes without LIGO. It is not gravitational signals. And also, this is ordinary neutron stars without gravitational signals. Blue is the result of collision gravitational wave signals, LIGO experiments. Okay, you have see some black holes in lower mass gap here. You see it is black hole neutron stars, the neutron star here, black hole, the result is black hole. And there are some signals which are upper mass gap, so-called intermediate mass black holes, which is not expected in your models. Now I will explain what is our models and why we don't expect this. So it is all observation and LIGO and not LIGO, electromagnetic and all masses of black holes. Now, unexpected signals, what I told. First, intermediate mass black holes. As I told, should be mass gap in this range, and you already have even companions are in this range, and result is heavier. So, if your calculation of data is correct, then you have some black holes which are in mass gap region.
Why is that a problem?
Why is a problem? You have no model.
Well, but they could have been formed from a previous collision. Yeah. So
it is also a model. I will speak about this. It is also, you need some model to explain this. Then you have problem with these models also. Okay, I will speak about this. Why we have this mass gap? There is some processes of creation of black holes. They are so-called pair instability. If black hole mass is in this range, initial black hole, then neutral particles lose energy because they create electron-positron pairs. And you have instability, and then you have blow up, and no black holes should be in this range. So it is model. So for black holes, which is not supermassive, not light, just medium, at some stage, you begin to lose energy because of pair creation, and it begin to oscillate and blow up. And there is also pulsation pair instability, which is some part of black holes survive. They just blow up a part of core, part of the layer, and central part would create black hole. So it should be in this range. And direct collapse, so your mass should be more than 135 solar mass. So it is what people working with black hole with their semi-empirical formulas obtain. So they expect to have these two mass gap which observed for normal black holes. There's a gap in this point and for small one. So their models working well for ordinary electromagnetic black holes, but don't working well for LIGO signals. Now about this merger.
Wait,
The electromagnetic black holes, what is the observation of those?
Yes, you have supermassive black hole, or you observe, yes, you have accretion meter, you can calculate their mass.
Okay, so you're seeing like the accretion disk or something.
Yes, so yeah, you can calculate. You see by telescopes. You don't need LIGO detectors.
But you could imagine then that kind of biases you, like you're not going to see like very slowly rotating black holes. And you might be missing a lot.
So you have X-rays, black hole candidates, and you estimate their mass and put on this diagram. That's all. And then on same diagram you put the signals from LIGO. And for ordinary black hole, electromagnetic black holes, so-called, you have observed two mass gaps. And it was theory to explain why you have these two mass gaps. And it was power instability model and pulsation power instability. And it appears that you have not this in LIGO signals. Now, you can be merger, hierarchical merger. So you can go in this restricted region by merging of several normal black holes, normal, not in mass gap. So it is like this 92 like events, which is in Margap. It is merger rate should be half in volume gigaparsec cube per year. You expect half effect, half events per year. It is one events per 2 years maximum. And then to calculate, it is first generation, merger rate of first generation black holes, which you calculate from LIGO data. Then if you have triple objects, then how many of them survive, how they have mergers, they have this probability. You have this from experiment, as I talk from LIGO data. And to obtain observable, it is theoretical and it is experimental. So you should use very extreme.
It's constant in time. This is so. Why should it be constant in time?
What?
This.
It is not constant. It's just you have rate.
Yeah, but that's the rate today.
Yes, today.
Yeah, but what if the rate in the past was larger because there were more of them around? Once they collapse, you have fewer of them around. So if you want the rate goes down.
No, you calculate rate now, you observe now.
Yeah, but the ones that are in the gap were formed before. So when the rate was higher.
Why?
Why not? There were more objects.
Why was more objects? It was
because they've merged and they've went from 2 to 1.
To create binary system, you need time. But yearly it was less objects. Now are more. Opposite.
Well, that's not clear. That's not clear because the star formation rates were much higher. So the production.
Star formation rate, yes. But then you have stars, you need time to create black holes, you need time to have binary system, you needed time for collision.
You don't need much
you can calculate.
To make a 20 solar or 30 solar mass black hole, you don't need much time at all, right?
No, binary system and time of their collision. You can calculate how many black holes you need to, how many stars, then how many black holes, how many binary black holes, and how many of them have time to merge in this volume per year. And you can calculate.
But so, your difference between 0.4 and 0.6, I can imagine that the rate was twice as high.
No, but this was obtaining by these assumptions.
Right.
So look, you have 50% of this system, not binary, but triple systems. You say that half of them are triple systems. Then survival that they will survive. It is 60%, very high. And merger rate is also 20%. That's one from fifth, they merger. And you can then obtain this. So as I told, in price of very extreme assumptions. It is, as I told, this is not calculation. It is some experimental results. It is astrophysical people, astrophysics people who have some these formulas. Okay, so now about lower mass gap. Here is a lower mass gap. Here is the neutron stars. It is ordinary black holes, and it is mass gap. No neutron stars can be in this region, and no black hole also. So it should be mass gap for them. But you observe several such objects versus this 90025, which have binary neutron stars with 3.4 solar mass. So it's also possible explanation of this, how I can obtain such a strange object for our models. And also next unexpected event, we have binary system. One is black hole, and another object we don't know. It is black hole or neutron star. Also, these masses again come from calculations. We don't see directly. We have these chirp-like signals, and we have model to calculate, extract mass from these signals. So we have these signals which are heavier than pulsar and lighter than any black hole. So if this calculation is correct, this signal also is not expected. Now, as what kind of model we have to creating this binary object? It is primordial black holes, probably we have, but we have restriction by CMB data and micro lensing, and also so we have this restrictions on primordial black holes, and then astrophysical binary systems, how they was creating. There are three possible mechanisms, and you can calculate this rate of these binary systems. Okay, you are very tight. I will be finished soon. And all these mechanisms predict that binary black holes theoretically should be 510 per year in this volume. But observable is more than 5 times larger from LIGO data. So it is one of the result of this analysis. Now, how this merger was calculated? It is merger rate. It depends on number of black holes. It is some coefficients, which I don't go direct what it means. Number of black holes, also long formula. Mainly here is the star formation rate, which is experimental formula. That is the distance in redshifts, which working well for ordinary stars. And this function, like Gauss distribution, which is have maximum at z equal to 2, which is look back time around 10 giga-year for ordinary matter. So star formation rate was maximum at z equal to 2. So now problems of this standard mechanism that observed merger rates is higher than theoretical predictions. We have 90 events, but only one have electromagnetic counterpart. But we expect to have, because binary neutron star should already be accompanied by gamma ray bars. Also, black hole neutron star probably should also emit gravitational radiation, and black hole, what we see and what we expect can be accretion by some matter, also should emit electromagnetic radiation. And also we have this mass gap observers objects that we cannot explain. So our suggestion that this signal may be emitted from mirror world binaries. Mirror world we told before. So why we expect it is now died about mirror world if this exists and it was created by Big Bang but with lower temperature from different papers. I not mention them. That we have constraints. The temperature should be half of hour, and the mechanism of lithogenic giving baryon number in range what we observe, and we can explain the dark matter around 5 times, and we see that helium in the mirror world should be much more than our. We have 20% helium, 25, and they will have 75, 80. If you have huge, massive helium stars, they are more massive, evolve faster, and we have big galaxies which have form of sphere already formatted by this massive object. And then in calculation, in this analysis, astrophysical analysis, this helium evidence that the initial mass function will increase it in 1.5. The star formation will begin much earlier, Z equal to 10. It is almost a Big Bang, 13 in our world, 13 giga a year. And the star formation rate is 1.3. And number of stars almost 5 times, so in mirror world. And number of black holes more than 10 times more in mirror world. If you insert this number in models of creation of binaries. So combining all these factors, it is rate in mirror world. It is 10 times roughly more than in theoretical in our world. So it's better explains LIGO signals. Also, hierarchical mergers are more probable because we have more stars and they are more dense, and can explain these gap events. Also, it's easy to produce heavy neutron stars in lower and supermassive. So it is empirical formula. Go to conclusions. So in the mirror world scenarios, number of binary systems is higher. Black hole merger rate amplified is in range of LIGO estimations. Mass gap event could be better explained, and most natural result is that no detection of electromagnetic radiation. Because we have mirror photons, you don't see them.
Why don't the mirror black holes form ordinary accretion disks?
They have formed.
Well, but then you would have an electromagnetic signal the same.
Explanation why don't see electromagnetic signal, because after collapse, you form a more massive black hole which follow everything. Not.
But that would be the same.
No, but it depends if you have neutron star, one of the companions, but if you have wide binary object, which is
no, but we're talking about. Your point was that it's for black hole, black hole, the electromagnetic signal.
Yes.
Because if you're talking about neutron star, there's only 4 events. You see one. It's not such a. But if you say that there should be
an electromagnetic signal for essentially all of the events, and you have 90 of them, and you don't see only see one, then you see.
But if you result, you have big black holes, then you expect, okay, probably this final black hole just not emit anything because all matter was swallowed.
That be the case for ordinary?
But they are not massive black holes. What you observe in lower gap and middle mass.
Okay, but that's just for the few that are in the gaps.
Yeah, so you can see, you see one, but probably you should see more. But if it's a mirror, then okay. You principally cannot see anything because even if it's accretion disk with normal matter and you create black hole, it's small accretion disk because mass of mirror matter is 5 times more. There are more massive objects.
No, but you said that there were only 2 NS events, right? Observed.
Yes. Not observed. Legal,
so it's not very conclusive if one of them is not accompanied by electromagnetic radiation.
Yes, but you see black hole neutron star.
For instance, 20 NS events, and then 1 or 2 of these.
Okay, it is prediction.
This would be a more compelling.
Okay,
evidence, right?
What I say, we have not enough data. We wait for next run.
Okay.
It is predictions that we say that we will see more, and only 1 from 10 will have electromagnetic counterpart. It will be in our world, and 10 will be in mirror. So you will have data around 20, and you have 2 with root with counterpart and other not. Then what you can say, how can explain this? Of course, if you have black holes, then you can say, okay, black holes follow everything after collision. But there's the neutron stars, black hole neutron stars, and light black holes.
So if there are 20 neutron star events, and 18 of them have electromagnetic signals,
then this model is not called.
Actually, our location is quite bad. Maybe we just don't have data because we don't know if the telescope is wrong, and we don't know where it is.
Right.
Okay, this is this references where this result was published. And thank you. Hopefully you're not tired too much.
Thanks for the seminar. But before I ask any more questions, I forgot to welcome our postdoc, actually, Sarah. That's Sarah just arrived, all the students, postdoc, faculty, and postdoc just arrived. Okay, I forgot to mention that at the beginning. Any more questions for the seminar? Yes, Andre.
Yeah, I'm still a bit confused with this idea because if you say that this mirror ball is like almost outward, then it means that, and it forms dark matter, right? Yeah. Then it means that most of the dark matter is in the form of stellar mass objects, right? Which is stars, mirror stars, even heavier in general, as you mentioned. But then I thought that the possibility that all of dark matter is in the form of massive astrophysical compact objects is actually ruled out from lensing.
No. So there's I understand. So you have clumping, you choose these clumps. So of course, about the first weak place of this model, but people working on this dark matter model, they calculate this. You have a lot of dust. Of course, you have stars, but you cannot distinguish on this distance. So they say that it's past this astrophysical test.
Okay, so stars, mirror stars are not 100% of dark matter. A significant fraction is also in the form of dark dust and dark gas.
Yes.
Okay.
We have small object, large object. You have you want to explain even machos. So in our galaxy, so you have stars.
But machos can be 100% of dark matter.
Yes.
Okay. Because
and also in hollow. If in hollow you have stars, how you can see this?
Oh, most probably there are stars, just little stars.
You cannot see micro lensing in Hubble.
Yeah.
Micro lensing you can see in the center of galaxy. So I'm not author of this model, but okay, somehow they want to explain that it's not against.
Also, this should be similar to the constraint for primordial black holes, which you mentioned, right?
Yes, it is from CMB.
I think it is also from lensing.
From lensing, micro lensing and yes. CMB, yes.
But that cannot be like stellar mass black holes, primordial black holes, or whatever black holes cannot form.
If they were, it should be very small.
Yeah.
So how do you get mirror black holes in the black hole mass gap? Are you claiming it's just because they start with some higher?
No, you have more black holes and you have hierarchical energy. More probably in mirror world than in our.
Vibrates.
Because to explain in our world, you need very strict assumptions. Because formulas are 50%, 60%. In mirror world, you don't need to just say 1/5 or 1/10 of this.
Okay, just
number of black holes and number of stars much higher than 10 times.
So will this mirror world change our estimation of the stochastic background level? Because if we assume there is some similar process in the very early members of that mirror world,
it would be 5 times higher.
Yeah. So the actual
there would be 5 times as many supernovas from the past. So
I mean, even bubble collision and first order transition or something like that.
Well, no,
okay. First order fast transition in mirror world, I don't know.
No, but the stochastic background from supernova would be 5 times higher.
So maybe.
Huh? 5 squared. No, the supernova is just it's like a decay. It's like a decay.
Mergers.
Yeah.
So we actually much easier to observe background if this really exists.
Yeah. Well, the background exists, right? Because we know supernova occurred, right? So there is a stochastic background. This would be a higher stochastic background.
So it is just very economic possibility to explain many astrophysical events without any extra assumptions, just mirror work.
That's a big assumption.
Well, that's
okay.
No, but I mean, it's much better. Yeah, you
it's more easy left and right.
Yeah, then
to introduce some string.
It's just a different assumption. Okay. Well, actually, just because now to get everything cooler by this factor of a half or whatever that you need. To do that, you presumably have to change the interactions, right? The interactions in the mirror world are not exactly
somehow. I don't know. I have no
yeah, but
yes.
And then the question is how that's going to change other things.
You have a lot of parameters.
Yeah,
a lot of parameters. Of reheating. It's not exact particle interaction. Maybe some other parameters. Well, maybe gravitational constant a little bit different. Or cosmological constant
no, not the gravitational constant. That you don't want to be different because that's the one thing that's.
I don't know.
Well, but there's no mirror gravity, right? You don't have mirror gravity.
You need inflation and reheating. And what you observe is everything after this. You already have
supposed to thermalize, right? But that's the whole point. If it thermalizes, I don't know. It'd be interesting to understand what it would take to get the temperature.
No. So to have inflation, you have scalar field with their interaction and something. The same you need to have mirror.
Right. Okay. So you reheat to a different. You reheat to a different temperature. So everything starts out.
More strange. You'll be same temperature, just different.
Yeah, but no. One in photon just
mirror for other. No.
One in the mirror and one in L. Well, you don't even need that. You just have to have branching ratios.
Maybe
photon reheats a little bit differently to ours because it has to thermalize. So if the density is produced, you get different reheating. That's not a problem. It's a different populations of particles that come in.
To explain parameters by anthropic principle, Even more,
Well,
more realistic. It's very different. What are you saying?
But you have no correlation with particle physics experiments, right? Because your mirror world is completely.
No, we have particle physics experiments.
But you don't have any correlation, right? With form of black holes, neutron stars, let's say, predicting the mirror partner as T. Right?
No, there's the experiments in neutron disappearing.
Oh, you're using it, but no LHC type experiment.
No.
Okay, I think we better stop it there because Merab is still here the rest of the afternoon. Let's thank him again.
I think the first thing that
One person.
Yeah,
Yes, okay, one person.
That's